Let me begin the discussion on relative velocity by making this statement. The velocity of an object is relative to a given reference frame. Usually the reference frame is the Earth or the ground, but that's not always the case. As an example to help explain this, say a person is standing on the ground and sees an airplane flying overhead. From the person on the ground's perspective, the plane is flying at, say, 200 meters per second. So we would say that the plane's velocity is 200 meters per second with respect to or relative to the ground or to the Earth. And then, let's say a kid on the plane throws a ball toward the front of the plane, and from the perspective of the passengers on the plane, the ball has a speed of, say, 10 meters per second. But from the perspective of the person on the ground, the ball has a speed of 10 meters per second plus 200 meters per second, or 210 meters per second. So that's the basic idea. Sometimes it's more useful to discuss the velocity and associated motion of an object in one reference frame rather than another. So we need to be able to convert the velocities between reference frames. In some scenarios, like the ball on the plane, this is not too difficult to do. But in other scenarios, especially when angles are involved, it's a little bit more difficult. So I will provide a procedure to help with this. I'll use the plane example to explain the procedure. The first thing we need to do is to write down these velocities in a particular format. For example, the velocity of the plane relative to the ground is written this way, where the p and g subscripts on the velocity vector represent plane relative to ground, or plane with respect to the ground. And the velocity of the ball relative to the plane is written with bp subscripts, and the velocity of the ball relative to the ground is written with bg subscripts. And now let's come up with a formal way to do the math. We already determined in this fairly simple scenario that the velocity of the ball relative to the ground is 10 meters per second plus 200 meters per second, or 210 meters per second. So using the velocity variables we just listed, it would be written this way. And so here's the key to this process. In this equation, there is a pattern to the way the subscripts on the vectors are arranged. Notice the two inside subscripts here are the same, and the two outside subscripts here match the subscripts on the resultant vector here. So that's the basic pattern. To generalize it, we might write it with ABC subscripts like this. This technique for dealing with relative velocity in one dimension works perfectly in two dimensions as well. Notice that the velocities in the equation are vectors, so we just have to be careful to do the vector math correctly when in two dimensions. Here's a procedure to follow, and then I'll demonstrate the procedure with a two-dimensional example. Draw a picture showing the velocities involved with appropriate subscripts, list the velocities, and fit them into the form of the equation that looks like this. Solve the equation for the unknown velocities, being sure to use proper vector math. So now let's work through a two-dimensional example. A small boat is in the Gulf Stream where the current is 4 miles per hour due north. The boat points directly east, perpendicular to the current flow, and travels at 8 miles per hour relative to the water. What are the speed and the direction of the boat relative to the Earth? When we write that, measure the direction of the angle that is east of north. So this is a two-dimensional example that's actually not too difficult because of how I've chosen the angles. There are other examples posted on Moodle where the angles are not quite as convenient and require a little more work mathematically. Okay, so back to this problem. The first step is to draw the picture. Let's start with the coordinate scheme, which should be written in terms of compass directions in this particular problem. And then the velocity of the water current is 4 miles per hour due north. So I've given the velocity subscripts WE for the velocity of the water relative to the Earth. And then the boat is going 8 miles per hour relative to the water. So I've given it these subscripts. And what we're trying to find is the velocity of the boat relative to the Earth. So I've written it VBE. Now, per the procedure, we want to arrange these three vectors so that their subscripts fit the pattern. The resultant equation then would be this. Make sure you can see that the way it's written here fits the pattern. Now let's plug in the values. In Cartesian form, the known vectors in the problem would be written this way, which gives us a velocity for the boat relative to the Earth, that's this, 8 and 4 miles per hour in component form. Now we just need to convert it to polar form to answer the questions in this particular problem. To do that, let's put the vector on a coordinate grid using the points of a compass. And now we can get the magnitude of the boat's velocity, or its speed, with the Pythagorean theorem, which is 8.9 miles per hour. And then for the direction, we're told to use the angle that is east of north. So that would be this angle. So to get that angle, we can solve this triangle, where we can now see that theta is the inverse tangent of 8 over 4, which is 63 degrees. So now we can finally write down the velocity of the boat relative to the Earth like this, 8.9 miles per hour, 63 degrees east of north. So that's this basic example demonstrating the process. As I said, there are 3 worked out examples on Moodle, and those examples are a little more involved than the one we just worked, so you should definitely review them. Also, I want to make a comment about those worked out examples. At the time they were written, a different textbook was being used in the course, and that textbook organized the vectors in the relative velocity equation a little differently. The form of the equation I presented in this video is this. However, in the worked out examples on Moodle, the vectors are moved around in the equation so that it looks like this, which looks different at first glance, but algebraically, as you should be able to tell, they're actually the same equation. I just didn't want you to be confused by the order of the vectors in those examples. Personally, I think the pattern discussed in this video is the easier one to use. Okay, so that's it for this video.